So the first question on the test was a multiple choice question, which was answered pretty well, though they catch a few of us out. What you've been given here is a Born-Haber cycle. Now the Born-Haber cycle does look a wee bit different to how we normally see Born-Haber cycles, which might put us off a wee bit. And from the question, what we're trying to do here is from these labelled steps, which we've not been given their proper names, just Roman numerals for them, we have to work out which ones are exothermic. Now, some of you maybe just looked at it and got it correct just by looking at it very quickly, though you can do it a bit more systematically. And probably what I would suggest doing, if you find this hard, is actually try and work out what each individual step actually is and label it. So if you look at the bottom, we've got NaCl solid going to gaseous ions. That's just the last enthalpy, so we can label that as lat. And going the other direction, we've got the elements in their standard states going to the compound. That's always an enthalpy of formation. Now, enthalpies of formation, generally speaking, are always exothermic, so you can't get the odd exception, which might be endothermic. But for now, we'll maybe put that as maybe one of the exothermic reactions. With our next step, we're going from solid sodium to gaseous sodium. That's an atomization energy. Atomization is always endothermic because you're breaking interactions apart. And in this cycle, they've gone a slightly different order than what we normally do. They've actually turned the chlorine into atoms at this point before they've done the ionization energy. But anyway, that's still an atomization energy of chlorine and still endothermic, so not worry about it. This next step, we're going from gaseous sodium atoms to gaseous sodium ions. That's the first ionization energy of sodium. And ionization energies, you're always taking electrons away from atoms. That's always endothermic, unfavorable. And then the last step of the cycle, we're taking chlorine and adding an electron to it. That's the first electron affinity of chlorine. Electron affinities are always, well, the first ones are always exothermic because you're forming a new interaction between a negative electron and a positive nucleus. So analysing all our steps here, last enthalpy is endothermic, atomization energy is endothermic, ionization energy is always endothermic. So the only two we've got for a question are the electron affinity, always stands out as being exothermic, and formations, whilst I said you can't always guarantee they're exothermic, in this particular cycle it's the only other thing that can be exothermic, so let's go for it. So we're saying 1 and 5. If we look at our options in the multiple choice question, we see the first option is actually 1 and 5, so that is our correct answer there. Question 2, giving you information about barium chloride. It's giving you an enthalpy of formation for it. It's also giving you some other enthalpy changes for it. So it looks like we're shaping towards a Born-Haber cycle. But before we have to do a calculation, what we have to do is define some energy changes or enthalpy changes. So we're given 1 to 4 there, we have to just state what they actually are called. So the first one, we've got barium as a solid going to barium as a gas. That's just a straightforward one, that's just the atomization energy of, enthalpy of atomization of barium. Now the trick in this question comes in the second one. We wouldn't normally give this as one step. So it's barium going to barium 2+ with 2 electrons. A few of you kind of picked up that was something strange about this, but we called it the second ionization energy. Isn't quite correct. The second ionization energy will be going from barium plus to barium 2+, because you're taking 1 extra electron away. Here we've got 2 electrons being removed in one go. What that means is we have to consider this as combining the first and second ionization energy. And I know we wouldn't really call that one enthalpy change, but it is the only way we can define this when you're moving 2 electrons in one step. So our answer for this one is the first and second ionization energies. Third one, have to be careful here as well. Now it's a standard change, but it's always easy to get tripped up by the diatomics. It's tempting to call this the atomization energy because you're breaking apart a molecule. But remember, atomization energy, you're forming 1 mole of an atom. In this case, we're forming 2. The proper way to describe this change is you're breaking 1 mole of bonds apart. This is actually the bond dissociation enthalpy of chlorine. Now you could get away with atomization if you said it was 2 times the atomization energy. That would be correct, but probably the easiest one is called the correct bond dissociation enthalpy. Last one is another kind of standard one. It's the electron affinity of chlorine. You probably should call it the first electron affinity, but I think the mark scheme allowed you just to write electron affinity. when you're adding an electron to a neutral atom. Okay, so we've got our energy changes defined now. Now we have to do a wee definition work, explain what's meant by the term Lattice enthalpy. A few of you got caught out just by reading your notes wrong. I think in the first paragraph of the Lattice enthalpy notes, it says that Lattice enthalpies are specific to ionic lattices. That's true, but it's not a definition, that's just an introductory bit. If you look in the bottom of the first page, you'll see the actual proper definition of Lattice enthalpy. The proper definition of Lattice enthalpy is it's the enthalpy change when 1 mole of an ionic compound, or an ionic lattice, is converted to gaseous ions. Then we get to question 5. Calculate to 4 significant figures the last enthalpy of barium chloride. Now, a lot of mistakes in this question, even though it's a fairly standard Born-Haber cycle question. The issue I think we have is, again, it's hard to tell without seeing it working out. Even though this question didn't ask you to construct the Born-Haber cycle, I'm assuming a lot of you probably tried to do this without the Born-Haber cycle. Always, 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 even if it's not given as part of the working out or what the question is asking for, always plot the wee Born-Haber cycle to keep track of what your numbers are doing. Otherwise, it's very easy to get mistakes in your calculation. So I'm going to do that now to show you what you should have got for your Born-Haber cycle. So looking at, so it's barium chloride, so we'll start with barium chloride at the bottom, BaCl2, and it's going to start as a solid. The last enthalpy generally we put on the right hand side, we're splitting up into gaseous ions, so barium 2 plus, and 2 chloride ions importantly. Then we go to the right hand side, generally what we put first is the enthalpy of formation, so we're forming it from the elements in their standard states. So barium is a standard state solid, and we'll need a whole chlorine molecule because we need Cl2 for BaCl2. We'll go through our steps here. So the first thing we have to do is atomization of the barium. We need to turn it into a gas first. So Ba as a gas plus Cl2, keep it the same. Now I'm going to follow what they did in the question. They actually combined the first and second ionization energies of barium. So if they're given us one value, I might as well put it as one value on my cycle. So going all the way to barium 2 plus, keeping chlorine the same. But we've got 2 electrons here. Now I have to look at the chlorine, so I need to split it apart, turn it into individual atoms. I have to be careful, I have the correct number, so keep barium the same. Now it's going to be 2 chlorine atoms here because I start with a Cl2 molecule and breaking apart. Still got 2 electrons, and then we've got our electron affinities to get to the chloride ions. So in terms of putting numbers on that cycle from what they gave us in the question, so let's just look at what we've got. We've got the enthalpy of formation being minus 855. We've got the enthalpy of atomization being plus 175. We've got the first and second ionization energies together being plus 1500. We've got the bond association enthalpy being plus 242. And then our final step is where a lot of us went wrong. In the question they gave us the electron affinity being minus 364. The thing that calls out here is that we've got 2 chlorines. If you look at the equation in the question, they only give the energy value for 1 chlorine electron. We therefore need to double this value. So 2 times minus 364. So bringing it all together, so finding an alternative route to get the last enthalpy. So we need to basically reverse this arrow, so we can go plus 855. So the final sum becomes plus 855 plus 175 plus 1500 plus 242 plus 2 times minus 364. If we type that into calculator, we end up with a value of plus 2044 kilojoules per mole. It says 4 significant figures. If you actually think about it, that already is 4 significant figures because it's in thousands. So there's actually no real rounding to do here. So a lot of work for 2 marks, again, but it's very easy to get those wrong. Just make sure you always do, in your working out, do a Born-Haber cycle to make sure you're not getting mixed up. 2D hopefully wasn't too bad in life. That's what name is given to the cycle used to calculate last enthalpy. Try and be careful with the spelling. they probably would be a wee bit generous, but if it's too different, they probably wouldn't give it to you. It's a Born-Haber cycle with a hyphen between Born and Haber. Question 7, we go on to an enthalpy of solution question. Calculate to the appropriate numbers in living figures the enthalpy of solution of barium chloride. So this caught a lot of us out, I think probably because we didn't really know where to look for the information. So the thing about enthalpy of solution, again, always start with a wee cycle. So what we've got is barium chloride as a solid. The enthalpy of solution is splitting that solid apart and forming aqueous ions. The route we use to kind of work it out if we don't know what that enthalpy of solution actually is we go for the last enthalpy first, breaking apart, just making gaseous ions first. So Ba2 plus gas plus 2Cl minus gas. And then we hydrate our ions, in other words, put the gaseous ions in the water, and that'll get us some exothermic values for them. Okay, so we have to look at what we've got here. They've given us two values in the question to give us this looks like hydration values are going from gaseous ions into aqueous ions. So for barium it's minus 1309, and for chloride it's going to be minus 378. So minus 1309. Do you have to be careful here because I've got two chloride ions going to need to go for 2 times minus 378. Then I've got my last enthalpy. Now, we did give you every carry forward. You have to just use your value from the previous question. So the correct value is plus 2044. So if you did use the value and sort of showed that in your working out, it was fine. And then you're finding an alternative route around this Hess cycle to get from the solid to the aqueous ions. Luckily, the arrows are all kind of aligned in the correct way. So the working out is just plus 2044 plus minus 1309. Plus 2 times minus 378. Again, I have to be a wee bit careful with their signs here. That should come out as a value of minus 21 kilojoules per mole. And for the answer for that one. 2F, using the value found in A, explain my barium chloride is soluble in water. Now this one was tricky to kind of answer if you didn't get the correct value for the previous part. The key idea is the sign of that value. For something to be favourable for dissolving, generally looking for an exothermic value. We do talk in the notes about how the fact some endothermic ones can be favourable, but generally you're looking for exothermic. So it's as simple as saying that the enthalpy of solution value is negative, or you could say exothermic. That's all pretty much you need to say for that one more question. Final part, a couple of theory questions. Values for the last enthalpies of the calcium halides are shown below. Explain why all these values are positive. A few of us really overthought this one. It is kind of weirdly asked, but all it's basically asking is why are last enthalpies positive? In other words, why are they endothermic? At A2 level, it's not going to be enough just to say that, oh, it's just positive because they're endothermic. It's justifying why they are endothermic. Basically, if you think about what last enthalpy actually is, it's breaking apart the last into gaseous ions. So basically for 1 mark, all you're having to say is that it takes energy to break the ionic attractions or interactions or bonds in a lattice. So you're basically describing why it's endothermic in terms of you need to put energy in. You need to put the energy in to break the bonds apart. Then 10b, or 3b, suggests why the values of the last enthalpies for the calcium halides decrease as group 7's ascended. So that was covered in the notes. So you've got the trend calcium staying the same in all these ionic classes, but your ana and your halides changing. As you're going from fluoride down to iodide, you're getting less and less endothermic, so it's becoming easier and easier to break the lattice apart. Our justification for that is just the idea that the ions are getting, so the anions are getting bigger. The bigger they are, the less tightly they pack, and the less interaction they feel to the ions around them. It is one more question though, so all you actually need for the mark scheme is just mentioning the size of the ions. So the halides increase in size down group 7. And obviously you could and probably should go on and just clarify that that means that the packing's less tight or the charge density is a bit lower. But that's all you actually needed for the mark.